Okay, good evening.
Good evening, sir.
Good evening, sir.
Good evening, sir.
So, yeah. So today we are starting our second unit of your module. So Foundation in Automobile Technology, Unit 2, and we're going to complete this one in 2 sessions. So I'll be starting the session number 1 today. So let's go ahead and see what we are going to learn today onwards. Okay, so the topic of this unit is the principal operation of an engine, right? So basically it's about engine, and I know that you already have a basic idea how the engine works and what are the theories and how the components are working and all and all. So the whole idea of this module is to go around it and do the same things, almost the same things again, and at the same time add or give more information and give me more knowledge regarding the engines. Okay, so what we'll be discussing: classification of the engine, multi-stroke engines, combustion process of the engine, efficiency of the engine, engine construction, and lubrication system. Lubrication system. This system, it has to be changed. So yeah, today I expect up to like fourth point. I'm planning to discuss up to point number 4. Before I go ahead, let me just ask few questions regarding the practical. So, how was the practical? Have you watched the videos? Have you gone through the videos? Guys, have you gone through the practical videos?
Yes, sir.
Yes, sir. Sir, there are some small issues, sir. Very noisy, sir. Background noise and a lot of, in the video recording, sir.
Video recording. Yeah,
Yes,
the
sir.
problem is we actually recorded this like few months ago, practicals. We could not, because of the this was actually done before this travel restrictions start, so that's why the noise is there. Now we can't record again. At the moment we can't record again. So because of that, what I will suggest is just go ahead with the lecture practicals. I will try to arrange a discussion sessions with the instructor, or if not, right, if it is not the case, what I'm planning to do is once you come back to the uh, university before once you come back to the university for the exams and all, we can have like 1 week or something. We can take 1 week or something and just discuss the practicals again, right? So for now, just go ahead with the practicals. If you have any questions, you can just send it to me. I can actually answer them. I can actually assist them. So we'll go ahead like this, because otherwise the time is the problem. I can actually keep. I can just stop doing practice, so I can let this practicals. I can have the like practicals after you coming or something, but it will actually it will end up affecting you. So the best choice of the best action for now is to somehow, with the available resources, we just gonna have to continue. Okay. uh, we are still recording some practicals, but we have to give the priority that for the ones we did not record last semester. So last time, actually not last semester, last time. So because of that, I can't actually use the our instructors, or I can't actually use them to do it, because even with the travels restrictions, staff members, our instructors are actually coming by themselves. So with all these restriction and all the risks and everything, they're coming by themselves to do the practicals, video practicals. So and only one day they are actually allowed to come and do the practicals. So because of that, we actually could not spend another set of time again for the same practicals, and even if we do spend time, same problem will actually come up. The reason may be the construction work is going around on the second floor still, second and first floors. So still the noise is there. So what I suggest is just go through the practicals, and I'm pretty sure if you read thoroughly the lab sheets, you will be very you can actually get a lot of information, because I personally went through them and I prepared the lab sheets, another set of lab sheets. That's why you get like that. So I highly suggest you to do that until we come actually, we will be able to clear this up. Okay, right. Now we go ahead and start. Okay, so basically, first thing I need to actually explain to you is engine. So as you know, you have seen the engine, but you have seen engines. So basically, we have a lot of several types of engines. All of these engines, sorry, these engines are actually, what they do is they utilize or they convert chemical energy into mechanical energy. So what we use in the vehicle is the mechanical energy. What we put into the engine through with or as fuel is actually chemical energy. So the chemical, after burning the chemical, the combustion. So during the combustion, it actually radiates heat. That heat is actually absorbed by the combustion chamber, or that heat is actually the hose for moving of the internal or piston in the normal engine. So the same principle has been used in different engines, different types or different engine types. So all of these engines actually uh, utilize, all of them are working in the same pattern. In addition to that, so these engines which actually utilize, or which actually working around the heat of the combustion process is actually known as heat engines. So they are actually classified into, like, different classifications are there. Different classifications are there, type of fuel using, what sort of construction are there, where the combustion is happening. So different type of classifications are there. So when we discuss about our usual usual automobile engines, we actually only consider about two-stroke and four-stroke engines. Again, they can actually divide into petrol or diesel or any other fuel types, because there are so many other alternative fuel types we can actually use for these engines. The images I would actually like to point to you. So the first image, as you see, is just a normal internal combustion engine with a little bit of advancements also included inside the engine. The second image is actually something called a turbo jet engine. So it's actually a variation of the gas turbine type. So basically, these sort of engines are known as gas turbine, right? So currently, these type of engines are not inside or not used in the automobiles, but it was actually there was a thought about that and it was actually tested. So if you, and I think I discussed in the last presentation, if you can remember, there was 3 images on the last slide or something. I think the last slide. So there was something called Chrysler turbine car, so which was actually the first production. It was supposed to be the first production vehicle, but because of the fuel crisis, this and that was stopped. And ultimately, these engines are not as much as efficient inside of automobile, because so our driving conditions, usually the conditions we operating is are actually very different. So because of that, still we are actually stuck with the normal reciprocating or piston type engine. So there were some innovations to actually replace the diesel or reciprocating or piston engine, but still we are stuck with that because there were some issues related to them, which were difficult to actually fix with. And by this time, like if we consider by today, the internal combustion engine, sorry, again, piston engine, right? Piston engine is well over 100 years old, and 100 years old means 100 years of technology, 100 years of technological development is behind that. So because of that, these engines are very like very efficient. So just to give you an idea how much of efficiency is there in a normal engine, the most highest efficiency engines nowadays, right? Nowadays, highest efficient engines are actually used by uh, for what you call this Formula One cars. They actually use one of the most efficient type of engines which are not available for mass market. They cost each one is cost, I don't know, few millions. It will cost around few millions. Anyhow, the efficiency is over 30%, right? You might actually you might feel that 30% is not a good amount, or it's not actually, it's not. But these Formula One engine can go up to around 50% at the moment. But for a practical normal petrol engine, normal like day to day using petrol engine, it's up to around 30 maximum. It goes up to 30. In a Formula One engine, it goes very much close to 50. But if we consider the efficiency of these things, like few hundred years ago, not few hundred years ago, by the time they were actually started, let's just say the first vehicle for first vehicle, the 1 liter engine was delivering around half a horsepower, or around 350 watts, something like that, right? But nowadays we have engines which have around 1.6 liter engine that could actually deliver up to around 1000, yeah, up to around 1000 horsepower, right? 1000 horsepower means it's around 750 kilowatts, right? That's a lot. So the technology has been advanced a lot. So because of that, this uh, just moving out from this particular type of engines is not ideal, or is it, it's not actually practically possible at the moment, even with the electric vehicles, which we will be discussing in the later units. Anyhow, one of the main disadvantage of these two engine types is how they operate. So usually, if we consider normal automobile or normal car or a van or something, where we usually use is where we use it in the traffic. Usually we are always surrounded with traffic, so our vehicle speed is actually always changing. It won't operate at the optimum speed. It will engine RPM will actually increase, sometimes reduce. So that's varied, right? But engine like a gas turbine, even though it's very efficient, it's only efficient and it's only possible to use at a certain RPM. So they are efficient at certain RPM. So they can't actually accelerate and deaccelerate suddenly. So because of these reasons, this turbine engine did not actually catch on with the automobile industry. Anyhow, since the one we are stuck with those, since the one we are actually using at the moment is reciprocating engines or piston engines, we will be actually going into, and we will be going deeply into discussing about the piston engines, how they work, what are the systems like lubrication, fuel injection, and how these ignition systems, airflow is actually affecting all of these things. We will actually, not all, most of these things we will be discussing at this module. So primary classification of any type of engine, as long as it's using any fuel, is actually comes as external combustion and internal combustion engine. So external combustion engine and internal combustion engines are very easy to understand or identify. If an engine have a combustion process and uh, energy generation or mechanical energy generation happening at the same place in such an engine is actually known as internal combustion engine. But if you consider a steam engine, which is actually shown in the image, right, which is the one shown in the image on the top image. So yeah, so if we go here, so let me just give you a small extra, try to explain how this thing actually works. So even though this whole area is there, like a cylindrical part is there, this is not completely filled with water. So it's actually filled with some tubes which actually contain water inside these tubes. So there's a section, I think you can see it here, this is like a fire sort of thing, this is actually called as firebox. So this is the place where the combustion actually happens. So you put a coal in here and this will combust, the coal will combust over here and it will generate heat. That heat will actually flow through these tubes, right? This is actually called as a heat exchanger. So there's like tubes, and uh, some tubes actually contains water and some tubes actually contain have gas going inside, or the exhaust gas. So the heat is actually traveling through. So when the heat is actually traveling through these tubes, that will actually, or heat is actually traveling around the water tubes, right? So heat is actually traveling, or heat is traveling around the water tubes, uh, which ended up heating up, or which ended up boiling this water inside it, creating steam, right? Creating steam. So that steam actually being pumped up to this cylinder over here. So the combustion is actually happening here. The energy is actually mechanical, the chemical energy is actually manufactured or delivered or produced over here, and the mechanical energy is actually produced over here. So the combustion and mechanical energy production is happening in two locations. So that's why it's actually called as an external combustion engine. So in a normal automobile engine, it's completely different because the combustion happening inside the cylinder itself. So as a result of that, these are actually known as internal combustion engines. So once we come to these internal combustion, external combustion thing, these are actually known as heat engines. So there are all of these heat engines would be included into these two categories, external and internal. So for your introduction, as an introduction, I have included these things: steam engines, turbines, because turbines also the combustion is happening in somewhere else, and the turbine is actually rotated in a different location. It's not that much far, but it's two different locations. So in then we have internal combustion engine, which is the area we are actually considered about. So we have here auto engine, diesel engine, and vehicle engine. So auto engines, diesel engine and vehicle engine. I'm not sure whether you are familiar with these names, but auto engine means actually the petrol engine, diesel engine obviously is diesel engine. Vehicle engine is a type of a engine that can be run either diesel, petrol, hydrogen, or any type of a fuel. So we'll actually go through this, and we'll discuss like auto engine, diesel engine, and then we can actually discuss, or I can actually explain you how the vehicle engine works. So once we come to these internal combustion and external combustion engines, there are like advantages and disadvantages. If you compare these things, internal combustion engines are actually compact and more efficient because the combustion and the mechanical energy production is happening in the same place, and it will not actually end up losing energy in the process, and basically it loses less material, and most of the time the working fluid is mixture of air and fuel. So working fluid is the so it's actually a term that we used in thermodynamics, which you will be learning later. to explain the type of fluid that working inside of a system. So engine is actually considered as a closed system. So working fluid in that case is actually a air and fuel mixture. So since these engines actually have mechanical components inbuilt with the combustion, so these are actually known as these are actually easy to it's difficult, it's easy to start these engines. And internal combustion engines, since they are very compact and easy to operate, using them in automobiles is a very simple task comparing to the external combustion engines. Next, we move into something called a reciprocating IC engine. So, if someone say IC, that means internal combustion engine. So, it's the short term for internal combustion. That's why it says IC. So, the type of engine used in the automotive, type of engine used in automotive industry is actually a IC engine. So IC engines and these IC engines are actually reciprocating engines. So reciprocating engines means it actually has a mass actually reciprocating, going up and down, or going from one place to and returning back to the initial position and going back to the position it was before. So in a piston engine, it's actually, or an internal combustion engine, it's actually the uh, top position where the piston is actually moving, which is known as stop dead center, and the bottom position where the piston is going up to and returning back. So that is actually known as a reciprocating engine. So it's the reciprocating action of the cylinder, the action of this piston ended up having a mechanical energy. So that mechanical energy will be converted into a mechanical energy, or mechanical movement will be converted into a rotational movement using a mechanism known as crank slider mechanism. So crank slider mechanism is actually, if I explain to you crank slider mechanism, this section, right? This section is actually known as the crank slider mechanism. So that means you have a slider, crank. So this is the crank, right? So when this is this section, this is the slider. So when the slider is moving back and forth, so for example, back and forth means, so if this is a one position, we can go to another position. This comes up to here, right? So, right, and return back. So this is actually this process. So this this box sort of things over here, this is actually the slider. So if you turn it 90 degrees clockwise, then you have a piston moving up and down. So slider in the engine, or in a normal reciprocating engine, normal internal combustion engine, the slider is actually represented by the piston, and the crank, as usual, it's actually represented by the crankshaft, right? So this is the process actually, how a normal reciprocating engine works. So piston is moving up and down, so it is a reciprocating movement. That reciprocating movement is turned into a circular movement by using a crank slider mechanism. So in order for you to understand a little bit more about this crank slider mechanism and the reciprocating engine, I actually have put two video links. If you wish, and if you wish, and if you really wanted to learn more into this crank slider mechanism and how this internal combustion or the reciprocating part of the engine works, you can actually go ahead and follow these two links. Okay. So that's the basic idea. So it doesn't matter what the type of petrol is actually, petrol, what type of fuel is used. This is the basic idea of a internal combustion reciprocating engine that is actually used in a automobile, right? Okay. And I know actually, I actually know that you have learned these things, but I will just go ahead and discuss basic things also. But this point or this part, I don't think you have learned this. So even though we are actually using this whole process, or even though this is the mechanical section of the whole engine operation, there's a thermodynamic side also attached to this, right? There's a thermodynamic side attached to this. So there's a theory, right? There's a theory called Carnot theorem, right? The Carnot theorem. The Carnot theorem says no engine operating between two heat reservoirs can be more efficient than a Carnot engine operating between those same reservoirs. So a Carnot theorem is actually explain the thermal process of an engine. So it actually explains how how an engine is actually working, right? So how the heat is actually flowing and how it makes a mechanical work is done. So basically, in the term, Carnot cycle is very complicated topic. It's actually simple, though it's actually complicated. The basic idea of the Carnot cycle is to generate or is to come up with the theoretical cycle to explain how the heat engine is actually working. So if we consider any heat engine, any type of a heat engine, all of these heat engines actually follow this process one way or another, right? So let me explain how this Carnot cycle actually works. So Carnot cycle is explained very simply like this. So it has a piston, right? Piston located inside a cylinder, which is actually shown by the working medium over here, right? Which is shown by the working medium. Just which is actually shown by the working medium over here, right? And it is actually connected to two reservoirs, right? It's actually connected to two reservoirs. So one of the reservoir is actually hot and the other reservoir is actually cold. And there are some conditions. As I told you, this is a theoretical cycle. The conditions are like this. So the working medium or the inside of this piston, right? Or inside of this piston that I have explained earlier. So that piston is completely insulated, right? So which means there's no way to heat to escape outside from inside the working medium. There's no heat is actually traveling through the walls of the cylinder, right? That's number one. Same, and the hot reservoir is having infinite amount of heat. So it doesn't matter if we take a certain amount of heat, it will not actually make any difference. Same thing for the cold reservoir, right? Same thing for the cold reservoir. It's also having a infinite amount of heat, right? Sorry, infinite amount of uh, holding capability in this reservoir. So what happens here is very simple, right? Very simple. Once this heat reservoir and cold reservoir is connected to the working medium, or in this case the piston, right? So if we hot reservoir and cold reservoir, if we turn on the hot reservoir first and let the working medium to work, then if we close the hot reservoir and open the cold reservoir, a work will be actually coming out, right? A work will be done. So the work will be done. I can actually let me yeah, how can I put it? So this is a piston, right? And the hot reservoir, I will use and cold reservoir. Since I used blue, I will use green color. Okay, right. So this is hot and this is blue. Next, and I forgot one thing. The cylinder is actually sealed, so there's no heat. So there's no heat transfer, right? So working medium is over here. So between the piston and inside the cylinder chamber, it's actually filled with working medium. So what we do is we somehow connect the working medium or the cylinder to the hot reservoir. What happened with the hot reservoir? So hot reservoir is in a higher temperature state, right? So when that temperature, since there are two bodies interconnected, the heat from the hot reservoir usually flows into the uh, this chamber, right? This chamber, that means into the working medium. So that working medium is actually getting heat, right? It's actually absorbing heat. When it is actually absorbing heat, it's started to move. It's started to expand. That expansion will create a force, right? Will create a force uh, towards downwards, right? Downwards, moving the piston down, right? Moving the piston down. And the piston will come up to the maximum position which it can move, right? Then it's stopped over there. As long as that happens, what we do is we actually remove or disconnect this connection. Then we add another connection. The next connection is actually, sorry, we connect the cold reservoir with the working medium. Now, since inside the cylinder chamber, it's in a hot state and the cold reservoir is in a lower temperature state, heat from the working medium actually goes into or it flows into the cold reservoir, right? Which actually ended up moving. This will end up moving the piston backward. So that means it will move other way around. So the piston will now move upwards. So I need to change the color again. Now piston is going upwards, right? So it will go upwards until it reaches the maximum position that it can move. As long as it can, once it comes to the maximum position, what we do is we now again disconnect this, right? The connection between the cold reservoir and hot reservoir. So once we do that, again piston will stop. Now it's in a stationary position. Now we go back to the first one, or the first thing what we did is we add temp heat again. So with that, the whole system will start to rotate, or the whole piston movement back and forth will be start. And the thing you have to understand is this heat addition and heat removing will start moving a piston up and down, right? So this is what we used to actually this is the same theory that we are actually using in our engine. So that actually happens over there. In addition to that, somewhat different from a usual engine that we are using is actually happening here. The thing what we have to understand is the heat reservoir is having infinite amount of heat, so it's never going to run out of heat, right? Same thing with the cold reservoir, it's never going to run out of heat cold. In addition to that, inside the cylinder, there's no way for heat to actually escape. So heat will always there. Whatever the temperature is there, it will always stay there. So because of that, this is an ideal situation. So there's no energy loss. If we give 100 uh, joules of heat or 100 joules of heat into the into the piston, we will actually get 100 joules work output from that, right? So that's why this is actually called as a theoretical engine, and that's what actually meant by this Carnot theorem. So basing on this theorem, there were few other cycles actually developed. So this is the theorem, and based on this theorem, we come up with the graph like this. Unfortunately, this is actually called as a entropy temperature graph, right? So entropy temperature graph, I don't, it's a little bit above your knowledge level, so you have to little bit learn about this, but you just have to understand how the Carnot cycle actually works. So the graph delivered or derived from that, which is the one shown here, is actually used to come up with the Otto cycle and diesel cycle, which are the cycles that we are at the moment using for petrol engines and diesel engines, right? And that's not all. This particular principle, right? This particular principle or the Carnot cycle is 100% efficient, and all the other cycles, there are so many few other cycles that can be used for engines, something like Stirling cycle, which there was a Stirling engine, and there were few more cycles. I'm not actually at this moment, I can't remember these names. So all of these cycles that used in the heat engines were actually developed from this particular theorem, right? So it's something you actually need to learn. So I hope you understood. Again, if you could not get this, if you were unclear about this, so I added like two links here. First one is actually a video tutorial. Second one is actually physics tutorial that you can actually go through step by step, slowly read and understand this. So yeah, I expect you will go through them and understand or get more detail into this. Um, Based on the Carnot cycle, there were two cycles were developed, mainly two cycles, Otto cycle and diesel cycle, which are the ones actually shown here. So these are actually not the 100% accurate one that we are at the moment using. These are actually known as the ideal Otto cycle and the ideal diesel cycle, but they were somewhat changed based on the mechanical or the based on the uh, practical limitations that we actually have in an engine when it is actually operating, and these the shape of the shape of the graph will be somewhat changed or somewhat dissolved with the actual engine. So 1876 the four-stroke based Otto cycle, and 1892 engineer Rudolf Diesel the developed by the diesel engine. Okay, so now we come to the Otto cycle. So I know that you understand the four cycles, right? I know you understand the four strokes. So this is actually known as the sequence, right? So in a petrol engine and a diesel engine, there's a difference. So petrol engines and the diesel engine, and the difference is petrol engine, you actually have to spark it, right? And in a diesel engines, you don't have to spark, it will auto ignite, right? It will auto ignite. So let us go ahead with the Otto cycle, and discuss about the um, we'll discuss about the diesel cycle next. So I'm not actually going to go through like what is suction stroke, what is compression stroke, what is power strokes, and what is exhaust stroke. So you already know what are these four strokes, and you already learn this in your practical session as well. So because of that, what I'm planning to do is, rather than wasting time on something you have already learned in your advanced level, as well as in your practicals. What I'm going to do is I'm just going to discuss about the graph. So basically Otto cycle and DC cycle or any sort of cycle like this actually uh, shown in a graph. So they so actually as graph. So this graph is actually showing how the pressure and volume is actually varying inside the engine. So it's like this. So I'm going to draw a piston in a combustion chamber. Okay. So this is the one position piston can be, other position piston can go. Second position piston will be moving up here. Okay. So what this does means is when the piston is moving from number one position, that means the, do I have to put like numbers? Number one position to number two position. It's actually number one position to number two position. What actually happens is the pressure and volume is the ones actually change. So in this case, the graph is actually drawn as when volume changes, how does the pressure change? That's how the graph is drawn. So the one actually in the x-axis is the parameter we actually change, and the axis on the p-axis, sorry, y-axis is the one will be actually changed. So that's the dependent axis or the dependent parameter of the x-axis parameter. For the x-axis parameter, the dependent parameter will be shown in the p. So y-axis, right? So when we actually move piston from 1 to 2, right? 1 to 2, the pressure will actually change. This is how, that's how this graph is actually explained. So Otto cycle is actually something called a constant volume cycle, right? Constant volume cycle. It's actually mentioned in the first one here. It's actually known as a uh, constant volume cycle. So we start from the zero position, right? Zero is where we piston is at the top position and it goes down. Suction or piston is coming down, which actually absorb air fuel mixer into the combustion chamber, and then piston will start to move upwards. So when the piston is moving upwards, that will increase the pressure. That's why from here to here, pressure is actually increasing. So you know the top dead center and bottom dead center. The lowest position piston is moving is bottom dead center. Highest position the move piston is moving as actually uh, top dead center. The distance between those two are actually known as stroke. No, you guys know this one already. So when the piston is moving from BDC to TDC, that means top dead center up to top dead center, the volume is actually reducing. So that's why number 2 to number 1 is actually coming backwards. So near back into the direction of the y-axis. Then at that point, the ignition will actually deliver. So ignition will deliver at number 2 position, right? So at number 2, compression stroke is actually finished. Compression stroke is actually finished. So at that particular moment, ignition will be delivered, and as soon as the ignition is delivered, suddenly the pressure inside the combustion chamber will actually increase because of the combustion and expanding of the gas within microseconds. So that's why this uh, line is going directly parallel to the y-axis. then it will reach its maximum, because at this point the piston started to move backwards down, so it's going down up to the BDC, right, which will reduce the pressure, right, which will reduce the pressure. But power stroke, at this point the combustion pressure is actually pushing the piston backwards, or it's pushing the piston downwards, moving the piston downwards, and it will go up to the maximum position that can actually expand, or that it can actually move. Once it reach there, your exhaust valve will actually open. So exhaust valve will open. As soon as the exhaust valve open, the pressure drops suddenly, right? The pressure drops suddenly. That's why there's a step like this, right? Step like this. So once the pressure drops suddenly, it at that point the pressure inside the piston, inside the combustion chamber, and the pressure outside of the exhaust valve is equal at this point, right? So basically at this point, in ideal case, it should be equal to the atmospheric pressure, because exhaust is open to the atmosphere. So once it open to the atmosphere, the piston is actually now started to move backwards up to TDC, which is actually pushing the the combust gas outwards within the same pressure, because it's open, the valve is already open and the piston is actually moving upward, so there's no compressioning is actually happening inside. So that's what actually mean by this, right? So 0 to 1 is the suction stroke, and 1 to 2 is the compression stroke. 3 2 to 4 is actually the power stroke, and 4 to 0 again is the exhaust stroke. So this particular operation actually shown very closely, very well again in here. But if you so the same thing that I explained is actually here. So 0 to 1, intake, compression, spark, Sunstone volume combustion. So at that time combust. So notice that at this time valves are closed, so as a result of that, piston will move. But if you look at the graph, you can see the one we discussed already over here, right? This is actually called as PV graph. So PV diagram here, and next to that, there's another one, right? There's another one, right? The one next to is actually called as the actual PV diagram. So actual PV diagram means the PV diagram which will we get if we practically draw a PV diagram out of an actual engine. So the difference you can actually you can, as soon as you saw it, you can actually identify the differences. So there's a lot of differences. The main difference being there's no straight line, there's no it's not like very neat, so it's more like a two loops. It's actually is two loops, one the one over here, the bottom loop is actually pumping loops, where engine or the piston itself absorb the intake or pump the exhaust out. So both of these things are pumping, so that's why it's actually called as the pumping loop. And the power loop is where the power is actually generated, so the compression and power stroke is happening in the pumping loop. That's why that section is actually considered as power loop, right? So the difference between these two were actually created by, or these are actually different from each other. The actual diagram is so much different from the theoretical one because of the real world situations that we actually have to deal with in a usual, in a normal engine, when the engine is actually operating. One of the things is pumping losses, which is actually known as when the pumping or the intake and exhaust is operating, the friction, heat losses, uh, any other practical differences. For example, something like where we can actually ignite. So even though we say the ignition will happen once the piston moves up to the TDC position, it's never going to work like that. The ignition will actually happen quite a bit before that. So there are some practical limitations. In order to make the engine work very well, we can't actually adhere to the theoretical PV diagram. So we actually had to come up with the actual PV diagram. So the engine was actually designed on PV diagram shown in the first image, so the theoretical PV diagram. Then after fixing the basic issues, we ended up having a PV diagram similar to the second one. So that's the one we actually used, right? Okay, so this is how the PV or the four-stroke engine is actually working. In the diesel engine, the only difference is actually comes in this 2 to 3 step, where it's actually not having a constant pressure movement. It's actually constant volume movement. It's actually have a constant pressure movement. So constant pressure will have a while constant pressure is happening. So more details, if you wish to go through, and if you need more about these things, would you like to learn more about these things, I highly suggest you to actually go through these two links. One is for reading and which explain all these steps very well, and the second one is actually as usual a video tutorial which is available in YouTube. So four-stroke diesel engine. So diesel engine also actually follow the same cycle. There's no same sequence, not the cycle, same sequence. So suction, compression, power, exhaust is the same sequence, but operating in a little bit different cycle. So if you look, if you move your attention to the graph shown to your right, 0 to 1 is as usual, but 1 to 2 is as usual, but 2 to 3 is somewhat different here. So somewhat different mean earlier, if you can remember, in the petrol, right, in the petrol engine or the Otto cycle, in the Otto cycle we had graph is somewhat like this. Okay, give me 1 second. Okay, yeah. So in a if I draw the same diagram for a, sorry, if I draw the Otto cycle diagram, it actually comes like this. So number 2 and number 3 positions are bit changed, right? Bit change. So the difference here being is actually difference between these two is actually as you can see over here. So in the Otto cycle, if we move to the Otto cycle, which is actually drawn in red, actually has something called a constant volume process. So constant volume is over here, right? This one is constant volume. So volume is not changing from 2 to 3, right? 2 to 3 step, volume is not changing. But in the diesel engine, 2 to 3, the volume is actually changing. Volume is actually changing, but it does not change the pressure, right? It does not change the pressure. So let we shall we like go through and let me try to explain how this actually works. Let me check the next slide. Okay, so there's an arrow moved. I have to fix that. Um, so for now, what I'm going to do is there should be a line like this over here. So it's actually what so it's there, but somehow it's moved in the graph. So it's here. So instead of just closing the whole window, I will just draw it by myself. Okay. Okay. So let me explain. So air fuel mixture in a diesel engine, air fuel mixture. There's no such thing as air fuel mixture. It's only taking. Okay, this is not a diesel graph. Somehow it's actually having a petrol or auto cycle graph. Okay, I will explain with this, and if you have already downloaded this, you may actually have to download it again from the LMS because there's a mistake. Anyway, so this is your piston, right? Uh, okay. TBC and BDC. So, right, we'll start from TBC. So now we are starting from intake stroke, right, or suction stroke. At the suction stroke, intake valve, how can I do intake valve? So exhaust valve, I'm drawing from brake, right? So what happens is intake valve is going to open. Once the intake valve, so piston is at the suction stroke. So intake valve open and piston start to move downwards, right? Piston start to move down, right? So it's moving down from TDC to BDC. So that means position 0 is over there at TDC. This is TDC. From TDC to BDC is moving. So air is actually sucked inside at atmospheric pressure. So once it come to the BDC, now piston started to move back again, right? Piston start to move back again. Pistons start to move back again from BDC to TDC. Piston move start from BDC to TDC. When it is moving from BDC to TDC, at that time intake valve is closed, right? Intake valve is closed and the pressure inside the chamber, right, inside the cylinder is actually increasing when the volume is actually, while volume is actually reducing. Once it come to point two, number two position, right? Number two position being TDC again, right? Fuel, that means diesel fuel will be actually injected inside the combustion chamber, right? Injected inside the combustion chamber. When that's actually happening, right? When that's actually happening, while that actually happening, pistons start to move backwards down from TDC to BDC, right? TDC to BDC. But since the pressure, fuel is actually introduced, it will actually start combusting. It will actually start combusting, right? It will start combusting, and up to a certain extent, that means up to like half of the length from TDC to the BDC length, that means stroke length, up to half of the length, even though volume is actually increasing, the pressure will be staying the same because the combustion is still going on and the expansion of the airfoil mixture is happening inside. So that's why we actually have this constant volume, constant pressure step here. Afterwards, once it's actually moved that point, from there onwards, when the volume is actually increasing, the pressure start to drop up to number 4, right? But still, it did not come up to the atmospheric pressure, right? It did not come up to the atmospheric pressure until we open the exhaust valve, which is over here, right? Once the exhaust valve is actually open at this point, the combustion pressure, the gas air fuel mixture will actually drop, or it will actually suddenly drop the air fuel mixture pressure up to the exhaust pressure. That means atmospheric pressure. That's why we again have this 4 to 5 step sudden drop over there, right? Then, as usual, uh, while the piston is moving backwards from BDC to TDC, exhaust gas is actually moving out, while the since the exhaust valve is open, there's no pressure change in this step, right? So that's how the 4-stroke diesel cycle works. I hope you understood. So the basic idea you only have to understand is point 2 to 3. So everything else is the same. Once the piston came up to the TDC position, the fuel will be actually injected in. Once the fuel is actually injected, the while once the fuel is injected, the piston is actually starting to move back down from TDC to BDC. When this actually happens, the pressure is increasing at the same rate the volume is increasing, right? So because of that, there's no pressure change in the actual graph, right? So but if you go to an ideal graph, it's not exactly like this, since the image shown here is not the correct one. Let me try to draw one just to give a brief idea. So bottom section is as usual for the previous one. Over here it goes somewhat like, it's not something like that. So it's somewhat different. Let me just share that proper drawing, proper image in the next slide. Sorry, this is actually the wrong image I have put there, so I will fix that. So until then, if you have any questions regarding this diesel injection or diesel cycle, you can actually go through this provided links and you can get more details about this. And the thing you have to actually remember, another thing, diesel engines are actually called as compression ignition engine. So diesel engines do not have a spark plug. It's actually the combustion process is actually started by delivering a pressure, delivering of the fuel into the already compressed air at point 2 over here in the graph. So once it since the temperature of the air is high at this position, because I'm not exactly sure, there's a equation called PV over T equals K. That means PV over T is constant. So whenever the pressure is increasing, that means volume will be actually uh, reducing, right? In turn, this will actually increase the temperature. So this at point 2, the temperature is very high at the point 2. So, and point 2, the temperature is actually high, and at that time when the fuel is actually injected into the combustion chamber, what actually happens is that its pressure goes even higher, uh, automatically igniting the fuel. So this is actually because of property of this fuel, diesel fuel. So we call it as auto ignition point. So for petrol fuel or the auto cycle or gasoline or petrol, it has a very high auto ignition point, but for diesel engine, it actually has a lower auto ignition point. So diesel engine, diesel fuel, even if you put a flame into the diesel fuel, it will not actually ignite until it get its operate, or the pressure it's need to actually ignite. So that's why these are actually known as compression. Sorry, these are known as uh, sorry. That's why these are actually known as compression ignition engine, because these are actually ignited by compression. So I will fix this image. Until then, we'll go to the next slide. So we discussed about the four-stroke engine until now. There's like disadvantages and advantages. So uh, let me just discuss. So these things actually have dedicated lubrication system, and since it's actually you have to submit provide fuel for every once for every 4 strokes, that means once for every 2 cycle of the engine. This will actually reduce the amount of fuel needed, and no oil in the combustion, so less pollutant and less clean air. And in addition to that, emission controlling is very easy, right? Disadvantages wise, since you need a separate lubrication system, it's expensive and a complicated construction, and needed more components, because you need actually valve system or valve train to operate valve. And engine always has to be operated in a horizontal position, where the lubrication system, since the lubrication system actually works on the gravity flow, right? It actually use the gravity to return the oil back to the oil sump. So it has to always used in this particular arrangement. But for two-stroke engines, we may actually be able to fix these issues. So diesel versus petrol, if we consider these things, the basic idea of this difference between these two is the compression ratios. For a petrol engine, uh, compression ratio goes from like 8 to 12. For a diesel engine, it's from 18 to 25 approximately. RPMs, yeah, diesel engine is very lazy engines, and their RPM is lower compared to the petrol engines RPM. The reason being low, diesel engines need a particular time to combust. So that whole process actually takes a own time, because it's not ignited. It will auto ignite once it comes to the correct temperature and pressure. So it requires a little bit more time, right? In addition to when it comparing with the petrol engines, since it's actually the combustion process is very fast, it can actually reach up to a higher RPM. And diesel engines are actually known to have a higher torque value. Torque means the uh, rotating force, how much of force it can actually, how much of force it can deliver when it's rotating. So that torque value is actually higher in diesel engines even at lower RPMs. That mainly due to the differences in the engine construction, because petrol and diesel engines need known to have a higher uh, higher stroke length, as for the reason being the compression has to be higher and it's need time to combust. So because of that, they need to have a higher torque length, higher stroke producing higher torque values. But once we compare the cost wise, basically maintenance cost is actually slightly higher in diesel engines compared to petrol engines. uh, uh, Usually both are very useful, and but finally it comes down to how much of power each one can deliver. Basically diesel engines are more popular as commercial vehicles than the usual passenger vehicles or automobiles, due to its rough nature when it is running, and low cost in the diesel fuel compared to petrol fuel, and petrol engines having more refined feeling with them because of the low vibrations, as they are operating at lower compression ratios. So two-stroke engine is actually very much similar to the operating wise, very much similar to the four-stroke engines, but instead of using the conventional valve systems, what they use is something called a transfer port, where and by using a transfer port and using a sliding valve system means, as you can see here, oh, sorry, I need to use this. Oh, okay, so the carburetor, the line coming from the air fuel intake port over here, and this is actually a valve, even though we never call it as a valve. The ones valves that we have in a four-stroke engine, we call them as poppet valves, but these are actually called as sliding valves. There's another type of valve called rotating valves. Right? There's another type of valve called rotating valves, which are not in function at the moment, but they were used very long time ago in World War II. Aircraft engines actually use these sliding valves, sorry, rotating valves. So this is more like a sliding valve where the piston itself is actually acting as a opening and closing for the valves, and you can, as you can see, when the piston is moving up and down, this section is actually closing and opening. So once this is actually open, the air fuel mixture comes over here and which goes to the crankcase, right? And once this actually open, the exhaust side, these are actually called as port also. So exhaust port is also closed. And once the piston is actually start to go downwards, once it goes up to here, once it closed, the air fuel mixture will actually pressurize and move up this way, right? So then it comes up to the combustion chamber. The combustion chamber, once it combusts, piston will again come back, opening the exhaust pipe, right? So that's how a basic two-stroke engine works. I guess you can understand, at least you have seen it. So this is the basic process of it, how it works. Uh, so air fuel mixture comes here and it goes up to the transfer port and it's actually closed, moving upwards, right? The air fuel mixture inside it, and it's actually pressurized and spark. Combustion will move downward. The piston will come downwards, opening the exhaust port, which will force the air to combust, exhaust gas to go out. While and once it reaches the bottom dead center, intake port is actually closed at that time, but the transfer port is actually open. So the transfer port is open. Air fuel mixture, the reach fresh air fuel mixture will actually reach, move into the combustion chamber at this particular moment. So basically, this actually combines two cycles, so suction, exhaust and compression into one, and yeah, exhaust and compression in one, and suction Now, one, I yeah. So the diesel type of engine is somewhat little bit different because it's actually have a small valve attached to them. The operation basically is the same. So I'm not actually going to go through this thing again, and I know that it's again in the uh, your lab sheets as well as in your laboratory practical. And I expect you have actually, all of you have gone through it. I didn't actually see how many of you gone through it. And make sure to submit the lab reports on time also. So two-stroke and two-stroke engine advantage, disadvantage. Basically, it's simple, low construction, power stroke for every revolutions, and can work in any orientation because of the lubrication. There's no separate lubrication. Lubrication has to be provided with the fuel itself. Since it's lightweight, the power, once it compare the light power weight to weight ratio, it's actually higher. And since lab delivered a lubrication system, lubrication cannot be controlled very well, so it wear out faster. And necessity of low addition and oil addition, which will create a low efficiency as well as high pollution rate, because pollutions could not be controlled because of the oil addition all the time without any control in the engine. So because of these things, mainly related, the things related to the low efficiency and high pollution rates, two-stroke engines are not much used in the automobile engine. So once you consider the four-stroke and two-stroke engines, uh, basically if we go about them, two-stroke engines are okay, but four-stroke engines comes uh, up with their superior characteristics, basically higher thermal efficiency, and it can actually control the fuel. It can actually control the higher thermal efficiency, low fuel consumption, low lubrication oil consumption, and in addition to that, low emissions. Because of that, two four-stroke engines are very popular, and with the new developed manufacturing technologies and designing softwares and applications available at the moment, the allowed the diesel engines, or the sorry, four-stroke engines to have even higher efficiencies and to deliver almost the same amount of power as a two-stroke engine. So at the moment, because of that, and other reasons that actually mentioned here, four-stroke engines comes up as the winner in this case. But it doesn't mean that two-stroke engines do not have any place in the world. It does actually, especially in places like small light engines are needed, for example like a snow blower, or something like a wood tree cutting machine, or lawn mowers. These are actually using these two-stroke engines because of their lightness and less components in them. So next we will move into the basic terminology, and I know basically you know about these things, and the top dead center and the bottom dead center, which is the section over here mentioned. In addition to that, we have something called clearance volume and the swept volume, also known as the stroke volume. So the clearance volume is the whole area or the whole volume between the top of the piston and the uh, top of the combustion chamber, right? So that means this whole area is actually your combustion chamber, right? Okay, we got, this is the whole cylinder, right? This is the cylinder. So the area uh, marked here with darker pink color is actually known as the uh, clearance volume. So clearance volume is the amount of uh, compression, right? Amount of compression that air fuel mixture is getting. So once the piston is actually moved from BDC to TDC, the whole volume inside the cylinder itself will be actually compressed into the volume over here, which is actually the clearance volume. So clearance volume is the space between the top of the piston and the top of the cylinder itself, right? So this is the clearance volume, and the swept volume is the whole area from TDC, or whole volume from TDC to BDC, right? Whole volume from top dead center to bottom dead center is actually known as the uh, swept volume. So when someone mean, if someone say like the total capacity of the engine is let's say it's a single cylinder engine, if motorcycle, let's say motorcycle, single cylinder motorcycle engine, if it says 150 cc engine, that means that the engine is having 150 cubic centimeters. So that means the volume of the whole combustion cylinder or the whole cylinder is 150 cubic centimeters. So that 150 uh, cubic centimeters is actually comes from the combination of the swept volume as well as the clearance volume. So this total volume is actually the engine capacity. So if you have 5 cylinders or 4 cylinders, that means you just have to take the volume of one cylinder by adding the clearance volume to the swept volume or stroke volume, then multiply it by 5. Sorry, 4, number 4, or number of cylinders. So stroke volume, length, so stroke volume can be actually find using this equation. I don't think we actually have to do this equation. So the bow means the diameter. So that's why it's divided by 4. Next, the compression ratio. The ratio of total cylinder volume to the clearance volume is called as the uh, compression ratio. So the compression ratio means the ratio between the total cylinder volume. That means uh, clearance volume, we add clearance volume into the swept volume, then we have the total cylinder volume. The ratio between that and the clearance volume is actually known as actually. So cylinder clearance volume. So again, so basically the clearance, the ratio between the cylinder volume to the clearance volume is actually called as the uh, compression ratio. So the equation is actually shown here, and how to get the equation also shown there. Next is petrol engine R is the varies from 6 to 10, and the diesel engine 14 to 12 piston speed. So this is how we actually find the piston speed. This equation is not that important because we will not going to be doing a lot of equations or a lot of calculation related to this. We will be doing certain small calculations, so that's why I'm going through this section. So in order to find how much of power is delivered, what sort of power, so there's like 2 different side of powers available. So in order to explain that only, I'm just going through this section. So you know that clearance volume, what is engine capacity or the cylinder capacity. Uh, so next section is actually the power. So before we discuss about the power, we need to have a small discussion about it. So as I told you earlier, we usually show the operation of the engine using a PV diagram, which is shown in the image below. So in a PV diagram, the area covered by the PV diagram is actually known as the work done by the gas, right? Work done by the gas, or the how much of uh, how much of power is actually delivered. So this ash colored area is the power is which actually delivered, or the work done, or how much of power actually it delivered. So the problem with this particular thing, particular power delivered, is it's really hard to measure, right? It's very hard to measure. The reason being, it's actually a dynamic thing, so it's always changing, so the parameters are changing. So there's no like a easy way to calculate these values. So it can be actually measured using a equipment called there's a equipment called engine dynamometer, which can be actually used to fix an engine into it, and we can actually find out how much power it's actually making. But before we go into that, in order to build an engine, we need to have a basic diameter or basic sense of the sizes or the engine capacity based on the power we actually required it to have. So in order to do that, there were some uh, discussions about that, and there were two parameters actually explained about this. So in order to find the power, it's not actually difficult in order to find the power inside of a piston, because the power is directly related to how much of pressure it's actually having inside the piston, and how much is the cross-sectional area of the piston, because that pressure acting on that cross-sectional area of the piston is how the power is actually uh, made in the first place, or the work is actually made in the first place. But unfortunately, as you can see over here in the pressure volume or PV diagram, that pressure is not uh, static pressure. It will change all the time, right? It will change all the time. So because of that, the getting a proper value is not possible. So in order to come up, as a solution for that, there were two parameters were actually explained, which are known as indicator mean effective pressure and brake mean effective pressure. So in order to understand this, you just need to understand first what is indicator power means and what is brake power means, which is in the next slide. But I will give you a basic idea about that. So when an engine is actually operating, right? Let's say we have like 100 watts, 100 100 units of power actually delivered, or on top of the, or 100 watts or 100 units of power actually released by the uh, fuel itself, right? 100 joules, let's say 100 joules. 100 joules is actually delivered by the fuel, right? That was actually delivered, and it was actually delivered to the piston top itself inside the combustion chamber. So then that piston has to move, and the piston will be in turn will move the crankshaft finally, or then only we will actually have the power, or the that if we say 100 comes in, we should actually come maximum, at least we should get 100 out of the crankshaft. But there are valves we have to operate, right? There are valves we have to operate. The cylinder has to overcome the friction, the oil system has to pump the oil, the water cooling system has to pump water, right? Ignition system has to need the electricity, so engine has to generate electricity to run. So in order to keep the engine running, this system has to be running. So that means energy will be actually waste, or energy will be spent on these components, right? Energy will be spent on these components, or these things to be handled. So when that actually happen, right? When that actually happen, or when this is actually going on, certain amount of energy will be actually used by these uh, other systems in the engine in order to keep it running, right? Once all of these energy spent on other systems and the waste heat and everything, so all the heat, even though the energy is delivered as 100 joules in the engine, the whole 100 will not actually be reached, will be turned into mechanical energy. Certain amount of energy will be actually wasted. So all after all of these things, right? After all of these things, then we will get certain amount of energy out from the uh, crankshaft, right? We will get a certain amount of energy out from the engine, right? So this energy, right, if we turn it into power with the time and all, we call it as the brake power, right? Brake power is the actual power that is useful for us. So that's the usable power for us. So that's the power out coming from the engine, and the amount of energy delivered to the top of the piston, right? If we consider, if we turn or if we convert it into power, the amount of power delivered on top of the piston or inside the combustion chamber by the fuel, right? The amount of energy released inside the combustion chamber by the fuel is actually, if we convert it into energy, that energy is actually known as uh, indicated power, right? So we have two parameters now, indicated power and indicated brake power. So the pressure, right? As I told you, pressure is not a constant in an engine, so it will actually change, right? So it will change. But if we consider this, if we can come up with the mean pressure, right? Mean pressure that is effective for us, that is actually known as main effective pressure. So what we came up with, there's a two parameters was actually introduced for to explain the energy delivered inside the combustion chamber, and they are called as brake mean effective pressure and indicator mean effective pressure. The brake, the pressure, mean pressure inside the combustion chamber at when or not at when engine is actually delivering a brake, a certain amount of brake power is actually known as brake mean effective pressure. And the in if we consider it with the indicated power, at that time the effective pressure we can actually explain it as indicated mean effective pressure, right? So these were actually calculated values based on graphs and practical values. Then only these were actually came up with. So for mathematical calculations, we will be actually using these things. So so in order to come up with the mean effective pressure, there's another diagram that you will not be actually concerned about. You don't have to be concerned about. Amount of fuel and ignition can be actually changed for a particular indicated mean effective pressure. So based on that mean effective pressure, the whole other sections of the engine can be actually designed. That means piston and everything can be designed for a particular mean effective pressure, right? Then for that particular mean effective pressure, in order to have that particular mean effective pressure, uh, fuel delivery and ignition can be designed separate. So by balancing these two, the engines are actually delivered, they are developed. So only thing you actually just have to be worried about the mean effective pressures, and just remember there how to explain these things, and just use them to find the engine power. So as I told you earlier, there's two engine powers. One is the indicated power and the brake power. So in order to find the indicated power, the equation is IMEP, the indicated mean effective pressure, into K into capital N into capital L into capital A into simple N over 60, right? So in here, capital N is number of cylinders, L is number of strokes, A is cross-sectional area of the cylinder. So with the bore, you can actually find out that. And simple N is the RPM, right? RPM, so revolutions per minute. And K is a constant where K is half, or K is half of 4-stroke engines and 1 for 2-stroke engines, right? So BEP or the brake power, IP or the indicated power. So both of these things you can actually calculate. So I'm not actually going to give any calculations now, but make sure that you remember these equations. We will do something called a, I don't know whether you have done like a tutorial class where I will give you the equations and the uh, questions, list of questions which you have to answer first and come up to the class. In the class, we will be discussing, you have to actually submit it to us first, right? You have to submit us to first. Then what we do is, uh, then what we do is we discuss it in the classroom, and then only we will go for the marking. So the difference between these two is, so you have the time to just explore everything by yourself and do the calculations by yourself. If you have any problems, you will actually come up with some solution. It's okay, the marks will not be the problem. With marks is not a big deal here. It will not actually affect your final grade that much. So the idea here is you just have to learn how to do the mathematics part. So if you try to do the calculation, if you came up with some problems, and then later if we discuss it, then it's actually better. So what I plan to do is, I will first give you the uh, set of questions. Then we will actually have a small uh, like one week or something. I will give keep like 1 week or something gap, so you have enough time to actually go through the questions and answer it and submit the answers. Once you submit, we will actually mark them, and we will be having the uh, tutorial discussion class. Afterwards, we will be returning them back to you with another set of questions. You will answer them also. You will send back them to us again, right? So then your problem, the what you reduce, what you lost in the first one, will be actually returned from the next one. So I will let you know about this one later. Okay. So next we goes to the mechanical efficiency. So mechanical efficiency, so mechanical efficiency is how much efficient the engine mechanically. So that's actually the difference between the brake power and the or the ratio between brake power and the indicated power, as you can see over there, because brake power is the energy we actually, or the power we are actually getting. Indicated power is the energy actually, or the power actually delivered into the combustion chamber itself. So thermal efficiency, we have indicated thermal efficiency and brake thermal efficiency separately. So as shown there, the mass fuel, it's actually related to the mass fuel supplied and calorific values of the fuel. Uh, Next we have relative efficiency, where is the relative efficiency is the ratio between the indicated thermal efficiency and uh, AR standard efficiency. So somehow AR standard efficiency equation is missing here. Yes, AR standard efficiency is this particular equation. You just don't have to actually worry about these terms, which you just have to know what to put in the term. So don't worry about this AR standard efficiency or this relative efficiency equations, because we will not be going into too deep in this. But the specific fuel consumption equation you actually have to learn. Specific fuel consumption means how much of fuel actually consumed for a particular of a particular fuel per certain amount of energy. For in this case, it's actually mass fuel consumed in kilogram hour. It's actually comes in kilogram hour if you use once you use this equation. So, and the other thing is, when you are using these equations, you always have to use the standard international standards units. Don't use inches or kilometers or something, just use millimeters, meters, actually meters. Everything is in meters. If it is a distance, it's a meters. Power is measured by kilowatts, not anything else. And when you are answering, you always have to actually put your unit, right? You always have to put your unit. Okay, so next is something called Vankel rotary engine. So this is a four-stroke engine. It's a four-stroke engine, but it's very somewhat different from a usual engine. It's not in the at the moment. It's very scarce because so in a piston engine, the main disadvantage is in a reciprocating engine. The main disadvantage is having valves which consume a certain amount of energy from what it's actually produced inside, and having a reciprocating mass. So a certain amount of mass is actually moving up and down means energy low. Most of the energy will actually wasted in moving this component. So uh, uh, so that's why most of the high performance vehicles have very light pistons and light components inside the engine to reduce the weight of the reciprocating mass. So when you have higher mass, the inertia of the item is actually increasing, which will uh, end up difficult to move the item, which will actually finally end up creating a um, which will end up making the engine inefficient comparatively. So uh, to like fix this issue, the Wankel rotary engine is actually introduced. So in the Wankel rotary engine also there's a shaft, eccentric shaft. This B is actually eccentric shaft, and the A is the rotor, right? Rotor. It's actually it's a somewhat odd shape. You can see it's actually almost looks like a triangle, but it's not exactly a triangle. So by the movement of its very unique movements create combustion chamber, a moving sort of a combustion chamber, and keep combustion happening while all four strokes happening at the same time. So the advantage of being is it's very fast, and because of the low weight of the item, uh, it's actually easy to operate. It's actually revs higher, but unfortunately, because of the loss of this reciprocating mass in the engine, it does not actually have higher torque value. So in order to compensate for that, it has to actually rotate at higher RPMs and deliver high RPMs and step it down with using gear mechanism in order to get higher torque values. These engines were not in use at the moment mainly due to uh, two drawbacks. One is increase wear in this. There's like, so you can see there's three tips are actually touching the chamber. So or we call this as the housing. So it's actually touching the housing at all times. So these are prone to wear out very fast because of that. And the second one is uh, it actually needs a lot of lubrication, which ended up having emissions issues. And in addition to that, these actually have a cooling issue, right? These actually have a cooling issue. The problem being, compared to a normal reciprocating engine, the whole combustion chamber or the whole chamber is not getting the same amount of temperature. As you can see, uh, only ignition, so the power is actually happening on this section of the engine, right? This section of the engine, where in this area it's actually getting hot more than usual. Yeah, so and but if you consider the other side, so exhaust and ignition side has higher temperatures, and intake and compression type has lower temperature. Yes. So because of that, two sides of the engine has to have two different cooling effects, but it ended up not having the perfect cooling effects and lubrication issues. It's consumed a lot of fuel or engine oil as well, and controlling emission became very difficult with these engines because of their high revving nature. But still, these engines actually came in quite a bit of vehicles. Mainly, most popular manufacturer for this particular engine is um, most most popular engine manufacturer, or the manufacturer of these engines, are Mazda. Other manufacturers also started, but because of the issues they stopped using it. Only Mazda was able to keep building it until like 2008 2012 or something. Then they also stopped because of the higher emission regulations available everywhere in the world now. So engine, this particular engine is good actually, not that bad. There are some practical difficulties, but because of their low, small size and everything, they are actually very compact, very compact and uh, very compact. And for us, they can actually have a higher capacity for a small engine. So usually what Um, so these engines were actually sold by Mazda in the RX-7 and RX-8 line out, and there were some buses and also use the same engine. And there's another advantage of these engine: they can actually run on any fuel. There was few modified to run on hydrogen also, and these were used in racing application a lot, but at the moment it's not in use in the racing. These were having a very unfair advantage because of high revving and low weight of the engine. Capacity wise also, they actually delivered for like a one usual one in 1992, around 1992, when the RX-7, the FDRX-7, we call it as FDRX-7 model, was actually released. It actually had around it was came with a 1.3 liter engine, which delivered around 320 horsepower, compared to the other engines in the Japanese market were having around 3 liter engine. But there's some controversy around this because, as you can see, what they say 1.3 is only, sorry, only this ignition section. So if you only consider ignition section, it's 1.3. But if you closely look, you actually have to multiply it by 3 in order to get the actual capacity of the engine. So it's, if it is 1.3, it's actually 3.9 liter engine capacity. So there's like controversy, and uh, you can actually find out more about this engine. There's a lot of research going on these engines in order to bring them back to use, but it does not seem like they're going to come back anytime soon. So I have attached some videos for you guys to look and go ahead and understand. There's a one video actually showing the operation of the engine very well through a slow motion camera. So I highly recommend you to watch just to understand how this thing actually works. Yeah, so for this whole unit number 2, I want you guys to actually do a group assignment, right? I need you guys to do a group assignment. So what I need you guys to prepare a presentation about multi-cylinder 4-stroke engine. So multi-cylinder only, so no Wankel engine, right? The report should actually, yes, should do this. So include parts of the engine, construction of the engine, working procedure of the engine, valve train operation, effect of the valve timing, uh, valve clearance, compression ratios, and intake and exhaust manifold, how they works, what are the effects of them. Those are the parts you actually have to cover in this particular section. So construction wise, why there are ribs in there, so what sort of water coolant channels, how they are working. So these sort of things you actually have to discuss. So I expect each group to have around 8 members. I think there will be 2 groups which will be having around 9 students per group. So I need them to be submitted. So all the presentations you can submit through LMS. Uh, I will let you know whether you have to do the presentation or not. So grouping, I think there's a question coming. Yeah, so I will come back to that later. Next. So yes, the deadline is 5th of July. So I just need someone, can someone please confirm whether how are you going to divide yourself? I can actually divide you into groups, but if I do divide you into groups, it's going to come uh, as a, what you call this, based on the attendance. But if you can divide by yourself, then I don't actually have any obligation. I don't have. I'm not going to involve in that. You can actually divide by yourselves. You just have to let me know which way you prefer. So I'll give you until Wednesday. So Wednesday you have practical. Before then, your you might have some WhatsApp group or something to discuss these things and discuss it, and let me know by Wednesday which way you want to do it. Whether I should break you into groups or will you be divided by yourself into groups, right? Yes, there's a question. Uh, Yeah, so when you're doing the lab, can we use the lab sheets theory part for our lab report, or should we add a theory our own? Well, you can add a theory your own, but if you add a theory by your own, that means you are doing some other practical, right? If you are doing the same practical, same theory, so there's no need to add another theory. You just can take the same theory. I guess what you mean is whether you can copy paste it. I guess that's what you're trying to say here. For that, yes, you can do that. But rest of the sections you can't copy paste. That's not allowed. So if you copy paste, so we have this parallelism software, so we can just put it in there and find out from who you actually copied. So I don't copy anything, even the discussion. So don't copy, just do it by yourself and make sure you don't copy. I'm giving you a very big relief here. But if you are not going to follow that next lab sheets onward, from next one onward, I need lab sheets to be handwritten. So if you don't need handwritten, if you don't need to do the handwritten lab sheets, make sure that you do not copy from others. You can type by yourself themselves. I don't mind typing. Yeah, that's it. So this is the group assignment. Make sure you start doing that, and in the next session we will be discussing another set of this.
Sir, excuse me, sir.
Is it better if we write lab reports from hand or type it? What do you mean by that?
Sir, excuse me, sir.
Is it regarding LMS? Yeah. Someone said
Sir, can we do lab report as a handwritten?
yes, you can. No problem.
Handwritten or a Word document?
Yeah, both are fine.
Both are right. No, sir.
Both are okay.
Sir,
Okay.
can you explain
Thank you,
what
sir.
are the things we have to include in the report?
That's what shown over here. Parts of the engine, construction of them, working procedure of the engine, valve train operation and effect of the valve timing, valve clearance, compression ratio, intake and exhaust manifold. But don't try to include like Carnot cycle or anything. Don't have to explain the Otto cycle either. Just explain how the piston 4 strokes. This is how it works. These are the valves. Valves are made of these material. Valve springs are made of these materials. Exhaust, oh sorry, exhaust manifold is like this. It's designed in this way for this reason. Something information like that is actually I need. Yeah. So LMS problem, yes, I don't have an answer for that. As long as I know you, your LMS accounts have been updated already. So if you did not do that, I can't actually give any excuse anymore, because I received an email from our IT section. So they informed that all LMS accounts has been reset, the ones you have informed. If you did not inform by then, I actually don't have any solution for that. So make sure you somehow submit the lab sheets. Or if you have any LMS issues, please talk to the IT section, so they will fix that. So if they inform that you don't have lab attendance, then sorry, you have trouble getting into LMS, then I will accept. But until then, I can't do anything, because some people are taking the advantage of this. And keeping your LMS with yourself is LMS password and username is a responsibility given to you. It's actually a privilege. Without this, we'll be having a lot of trouble these days. So because the problem comes is you are sending in emails, someone are sending in here, and emails also, you guys are not the only people who are sending emails. So there's like a lot of emails getting for us per day. So if I miss a lab sheet, how the hell am I going to find it again? So because of those reasons, I can't accept that. So make sure that you come up with some solution. Your representative, I think, may be able to come up with some solution. Talk to ICT and get the solution. Okay, that's it for today. I'll stop here. It took more than 2 hours. That's fine. Yeah, one more thing. Thursday evening, you don't have any class. You had construction some module, and I was informed that it was rescheduled to some other time. So I'm planning to take that time and finish the classes as soon as possible. So the theory part, practical will go as usual, but theory I'm going to take on Thursday and finish it off. Right. So Thursday evening I'm taking the class. So I will inform the time and the link and everything later. So until then, so we will be discussing the next part of this module Thursday. And so yeah, thank you very much. Good night all.
Thank you, sir.
Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.